Here's a question about a truck parked on a slope. Now let's go ahead and interpret this from a Newton's law framework. Okay, the truck is parked on a 7-degree slope. Since it's parked, what that's telling me is the truck is not moving, it's in equilibrium. We want to know how big is the friction force on the truck. So basically, what is the force between the tires and the road surface that keeps it from sliding down the slope? Well, let's go ahead and do some preparation. And for starters, what I want to do is I just want to draw a picture of the situation, okay? And then the first picture I want to draw is a force identification picture. So here's my slope, and it's a 7-degree slope, and I'm going to exaggerate this. This is actually a little bit bigger than 7 degrees, but that's going to make my pictures easier to draw. And then I've got a truck here parked on the slope. Okay, so my truck is parked on the slope, like so. And let's do a force identification picture. So remember, we're going to isolate the truck and think about the forces that act on it. Okay, what touches the truck? There's one thing. It's the road surface. The road surface exerts a normal force, and it also exerts a static friction force. Why static? The truck is parked. It's not sliding. It's not moving, and so this has to be a static friction force. There's also the long-range force of gravity. So I just have these three forces. Those are the only ones that we need. Next up, I'm going to draw a free body diagram. And in a free body diagram, it's going to make sense to make the x-axis be along the slope. So I'll make my x-axis be this way, and I'll have my y-axis be perpendicular to that. And you'll see in just a second why this is such a great choice. Now let's think about the forces that act on the truck and the direction that they act in. But first off, I'm going to put another piece of information on my free body diagram. The truck is parked. It's in equilibrium. The acceleration is equal to 0. And so therefore we can say the net force is equal to 0. And if the net force is equal to 0, we can draw our vectors accordingly. Now there's three forces at work. There's the weight force. And the weight force is directed straight downward. Okay? Now this angle right here is the same as this angle right here. So this is 7.0 degrees. There's two other forces that act. There's the normal force, which acts perpendicular to the slope. So it acts in this direction along the y-axis. Then there's the static friction force that acts along the x-axis, and this points up the slope. The friction force is the force that keeps the truck from sliding down the slope. And that makes sense because if friction went away, we know how the story ends. The truck slides down the slope. So this is making sense so far. Now, in order to be able to work with the forces, I'm going to break them into components, okay? And the weight force is going to have a y component, and the magnitude of the y component is just equal to the weight force times the cosine of 7.0 degrees. There's also going to be an x component, and the x component, Wx, is just going to be equal to the weight force times the sine of 7 degrees. I can also draw that component up here, but I usually draw it here because it's easier for me to kind of see the to see the angle relationships. So I can redraw my free body diagram, and I think I'm going to do that by looking at my components. Okay, I've got an x-axis and I have a y-axis, just as before. Okay, here's my x-axis. Here's my y-axis. And I've got four components. I've got a normal force, which acts upward. And by upward, I mean in the positive y direction. I've got the y component of the weight force, which acts downward, and so this way. I've got a static friction force, which acts up the slope. And I've got a component of the weight force, which acts down the slope, like so. This is my complete free body diagram. Now the net force is equal to 0. That also tells me that the sum of the x components of the force is equal to 0. The sum of the y components of the forces are equal to 0. And so as a consequence, I can make certain relationships. And I'm going to do that in my solve step. Now, the sum of the x components is equal to 0. And so looking at my free body diagram, I can just say that the x component of the weight force is equal to the static friction force. So Wx is equal to Fs. Oh, now that simplifies things, because what I'm asking for is, what is the friction force on the truck? Well, the friction force on the truck is just equal to the x component of the weight force, but the x component of the weight force is just equal to W times the sine of 7 degrees. And the weight force is just m times g. It's the mass of the truck times g. And the mass of the truck is 4,000 kilograms. G is 9.8 meters per second squared. And so m times g, the weight force, is 39,200 newtons. So the static friction force is just equal to this number times the sine of 7 degrees. And if we work that out to two significant figures, we get 4,800 newtons. Now I'm going to note something. This is approximately 12% of the weight of the truck, okay? It's about 12% of the weight. And that'll help me do an assessment. A 7% grade or a 7-degree slope is steep, but it's not super steep. And so we expect the weight to be a significant fraction of the truck's weight, but not a huge, it's not half the weight or all the weight or something like that. So 12% of the weight seems reasonable for a slope like this. It's going to be some significant but not huge fraction of the truck's weight. And so our assessment is that our final answer matches our expectations of how the world works.